Welcome back to Who Wants to Be a Mathematician. I'm your host, Mr. Hill, coming at you with some AP Calculus. And we're doing related rates. Woo! Related rates! Crowd goes wild! Last time we used implicit differentiation to solve some related rates problems. And this time we're just going to up the ante and continue with related rates, but do some more problems. Alright, so here we go. So here it is, a light atop a pole of 16 feet. A boy 5 feet tall is walking away at this rate. And what rate is the tip of a shadow moving? So let's draw a picture. If we have a little light post here, light post, and then we have a boy walking away, at what rate is the tip of his shadow moving? So let's draw where his shadow would be. His shadow would be over here. So at what rate is that moving? So we have something going on here. We're also given he's walking away at a rate of 4 feet per second. So he's moving here at 4 feet per second. So we got a couple things. We got a light pole that's 16 feet tall. We got a man that's 5 feet tall, and we got the distance here is changing at a rate of 4 feet per second. We want to know what this distance is changing. So let's simplify this down. Let's draw this as a triangle. So we know that this is 16, this is 5. We are given this value in here. Let's call it x. So this value inside here is going to be called x. We have our 5 value over here. And we want to know, let's call this y, how the distance of his shadow is changing. So we want to find the rate at which his shadow is increasing out. Well, that's just the rate at which our y value is increasing with respect to time. We know that we know that the rate at which our x is changing is 4 feet per second. So now we just need to come up with some way to relate these two things. Well, if you think back to geometry, when you had a triangle inside of another triangle, we could compare these two. So we have 16 and y is, when we want to compare it to 5 and y minus x. Well, we'll just call it y minus x because that's this distance in here. It's going to be our y value minus our x value. So we have these two triangles, and we know they're similar because they fit inside each other. So we want to know how they relate to each other. Well, 16 is related to 5, and our y is related to our y minus x. Actually, I set that up wrong. I'm sorry. I am going crazy. Our 16 and our 5 are related, so that means our y and our y minus x are being related. So we want to know how this kind of works out. So if we cross multiply here, so we have 5y is equal to 16y minus x. We want to find the rate of what this is changing, so we're going to take a derivative with respect to time of 5y is equal to 16y minus x. And we're going to get 5 dy dt is equal to 16 dy dt minus 16 dx dt. Well, now we just need to get the dy dt's on the same side, solve for that, and we'll pretty much be golden. So if we do some math in our head, we combine these two terms, we're going to get 11 dy dt is equal to 16 dy dx. So if I have 11 dy dt is equal to 16 dx dt, then this turned into dy dt is equal to 16 over 11 times our dx dt we know is our 4 feet per second, so times 4. And there we have it. dy dt is equal to 64/11 feet per second. So the trick here was knowing that we can compare two triangles, setting up our equation here, and taking the derivative. So there wasn't a whole like volume formula or area formula we could use. It was just knowing that we can relate those two shapes. So let's jump into another one. Here we got a cone-shaped icicle. Ooh, I love icicles. Those ices, so delicious. I'm actually gonna make that a little bit bigger. Ooh. So if we have a cone-shaped icicle that's melting. Oh, the poor icicle is melting. It's melting into this pool of water down here. And the radius and height are decreasing at a constant rate of 0.1 inch per second, 0.2 inch, respectively. How fast is the volume changing when the radius are these two things? So here we are. We have a radius decreasing at a rate. So we know it's going to be our rate. Our radius is decreasing at, so if you think of decreasing, it's going to be a negative rate, so 0.1 inches per minute. And our height is decreasing at a rate of 0.2 inches per minute. So there we got with two things, and we want to find out how fast is the volume changing. So we're looking for dv dt. This is what we want to figure out. Well, if we remember, you know, way back into geometry when we talked about shapes and cylinders and cones and all that stuff, we knew that volume is equal to 1/3 pi r squared times our height. So that's our formula. So we want to figure out how fast is the volume changing when the radius is 2 inches. So we have 2 inches, and our height is 12. So we got 12 inches. So we want to find dv dt. So let's take a derivative of this whole formula. I don't know why I just did that. 1/3 or pi thirds r squared h. We're going to take a derivative of this. So this is going to be dv dt is equal to pi thirds times. Now we have to do some product rule here. We're going to get 2r dr dt times our h plus our r squared times dh dt. And then we just plug in our given information. Well, what do we know r is equal to? R is equal to our 2 inches. What is the dr dt? Well, this is going to be negative 0.1. Our height is going to be 12 inches. R again is going to be our 2 inches. dh dt is going to be negative 0.2. So we plug that all into our calculator, and we're going to get negative 4.8. So this is negative 4.8 plus 2 squared, which is 4, times this, which is negative 0.8, all times pi thirds. So our volume is changing at pi thirds, pi over 3, times negative 5.6 inches per minute. So pretty straightforward. Find your volume, take your implicit derivative of this, and then just plug in your information. And bada bing, bada boom, there we are. So last time we had a ladder on the side of a building. So we have to have our ladder here, give it a little rungs going down. And we know the ladder is 20 feet. If the bottom of the ladder slides at a rate, so here we go, we know this is going at a rate of 3 feet per second. How fast is the ladder sliding down the building? So we wanted to find this. So this will be the change in y. How fast is the ladder sliding down? When the ladder is 8 feet from the ground. So this was our dx dt, and we called this distance here x. We called our green distance here y. And we got the answer of negative 1.31 feet per second. So, a little twist, find the rate of change of the area formed by the ladder, the building and the ground, when it is 8 feet from the ground. So, knowing a couple things, known things. We know dy dt, because we solved it last time, is negative 1.31 feet per second. We know our dx dt is equal to 3 feet per second. We know the ladder length is, the length is equal to 20 feet. We know x is equal to 8 feet. So now we want to find the rate of change of the area. So we want to find the rate of change of the area with respect to time. So we have to think of an area formula. Area of our triangle is equal to 1/2 base times height. Pretty straightforward. We're given our base, so this will be our base as our x. So we're looking for our height. And can we find our height using anything? Well, yeah. So we have this triangle, right angle, because we know it's the ground against a wall. We have this as 8 and this as 20. So we know 20 squared is equal to 8 squared plus y squared. So 20 squared, that's 400. And if we subtract off 8 squared, so minus 64 is equal to y squared, and that's 336 is equal to y squared, so y is equal to the square root of 336. Oh my gosh, I don't have a calculator. Trusty dusty phone, here we go. Oh gosh, square root of 336 is 18.3. All right, so now we have our y value, and what is our y value equal to? Our y value is 18.3, and we're going to call that our height. All right, so now we have all the information that we need. So we want to find the derivative with respect to time of our area. Whoop. And that's going to be 1/2 base times height. So derivative of our area with respect to time is going to equal to 1/2. And this is going to be product rule, so we take base times dh dt plus h times db dt. Well, we know 1/2 our base is equal to 8. Our derivative of our height, which is our dy dt, is negative 1.31 plus our height, which is 18.3, times our base, or our dx dt, which is 3. And we just simply calculate this out. And whatever you get for this lovely answer is going to be the derivative of our area with respect to time. So this right here, when you calculate it out, is going to give you something, and it's going to be in feet per second, and that's what you're going to get. So now we want to find the rate of change of the angle formed by the ladder in the ground when the ladder is at 8 feet from the ground. So we have the same problem. We have the same problem only now we're looking for our theta. So we want to find the rate of change of the angle, so we're looking for d theta dt. What is our d theta dt? So if we remember, if we go back up and get all our information, our x is 8, our y is 18.3. So we're going to have our x is equal to 8, our y is equal to 18.3, and then our hypotenuse is equal to 20. So we're trying to find out how is our theta changing with respect to time. Well, oh my gosh, cat, no, don't, ugh. Oh, that's so annoying. Cat keeps escaping. So we need to somehow relate these numbers with our theta. So if we know our theta is related in some way, oh, I don't know, let's do sine SOHCAHTOA is opposite over hypotenuse is equal to opposite 18.3 over our 20. So we want to obviously take the inverse of this. Oh, all right, and you're the cat. We'll continue this in class because there's only this one and a couple other ones. So we'll just pick this up where we left off. I gotta go get the cat.